In the last lesson, you saw that the force of air resistance in magnitude is equal to a constant multiplied by velocity to the first power. Probably redundant to write to the first power. We just say F equals BV. As a vector equation, we can say F equals negative BV. Sometimes you'll see it in the form F equals negative KV. So an object like, let's say instead of jumping out of an airplane, a skydiver chose to jump out of a helicopter. So at first, when he initially steps out of the helicopter, he doesn't have any velocity yet, so he doesn't experience any resistive force. So the free body diagram just shows mg. Now he falls and accelerates as he falls. So by the time he gets to this next position, he's gained some speed. And so there's some amount of resistive force pointing in the upward direction. And he falls even further, continuing to gain speed. At some point, he'll gain enough speed that BV will calculate to be just as great as mg. Well, no matter what, the value of mg isn't going to change, right? This person weighs the same no matter how fast they're moving. But the resistive force is velocity dependent. So at this point, if the two forces are equal in magnitude, then the net force is 0, the acceleration is 0, and we say that the skydiver has reached terminal velocity. By the way, we should make a side note of how unique this is in comparison with force of friction. Friction is another type of force that resists our motion, but it does it in a much different way than air resistance. Let's say you drag a block across a desk, same block in both cases. Put a little hook there so you can tie a string to it maybe and pull. And let's say in the first case you pull it so it travels with a speed of 2 meters per second across the desk. And you can read how much force, maybe you put a spring scale along the string and you can see how hard you have to pull to move this block at a steady 2 meters per second. What you're basically measuring then is what's the force of kinetic friction between the block and the desk. And now you try to pull it with a greater speed, maybe 10 times the speed, 20 meters per second, and you measure how much force is in the spring scale. Most folks would, in a gut check statement, predict that the scale reading in the second case is much greater than the scale reading in the first place. It must take more force to move it at a greater speed. But it doesn't. The force of friction is not a velocity-dependent force. We know the equation for force of kinetic friction. The force of kinetic friction is equal to the coefficient of kinetic friction multiplied by the normal force. And regardless of how fast you pull it, the contact force or the normal force between the object and the desk doesn't change, and certainly the coefficient of friction, how smooth or rough the surface feels, doesn't change. So friction is not a velocity-dependent force. Air resistance is. And so the equations that govern the motion of objects moving under the combined influence of gravity and air resistance are a bit unique from anything we've studied thus far. But you could maybe make a guess of what velocity versus time would look like for this person who jumps out of the helicopter. They gain speed only up until the point at which the force of air resistance is just as big as the force of gravity. At that point, the acceleration becomes 0. So, let's start by making a guess at what the graph of acceleration versus time would look like. Initially, gravity is the only force acting. So if the net force is mg, that means ma is mg. The m cancels out, and the initial acceleration then is equal to 9.8 meters per second squared. But we know in time the acceleration is going to go to 0. Well, the way in which the acceleration reaches 0 doesn't graph like this. It actually exponentially decays and approaches 0. So 0 is like an asymptote for the acceleration value. What about velocity or speed? Well, again, when the skydiver first jumps, the initial velocity is equal to 0, and the skydiver is accelerating all the way up until the moment at which they reach terminal velocity. So they accelerate the most in the beginning, right? Initially, there's only downward force. Partway through their motion toward terminal velocity, there's the same amount of downward force, but a little bit of upward force. So the net force becomes less in case number 2 compared to case number 1. There's still a downward net force, so there's still some amount of acceleration. It's just not as great. So the speed is still increasing, just not at as large of a rate. So the speed is increasing at the greatest rate initially, and then that rate becomes a little less, and the rate of increase. In other words, we're saying the slope of the graph of velocity versus time is getting less and less. Acceleration is the slope of the velocity versus time graph. And we can see here that the acceleration is becoming less and less. That means the slope of this graph should become less and less. It's always a positive slope. It just becomes less and less slope. And eventually, at some point, the slope is going to equal 0. If that's the case, then just as the acceleration asymptotically approaches a 0 value, the velocity asymptotically approaches a maximum value. And that maximum value is vt, the terminal velocity. The graph of vertical position with respect to time, well, let's see. If it were free fall, that graph would just be a constantly upward curving parabola. However, if we use this graph as our guide, let's think about it. Up until, well, it's hard to say exactly when it happens. It never really reaches terminal velocity. It just asymptotically approaches it. But at some point, the acceleration is so close to 0 and the velocity is so close to a constant value that our graph of position versus time is going to start out parabolic, and then at the moment in time that the acceleration is practically 0 and the velocity is practically a constant value, then from there on the graph is practically just straight line, right? So notice how these graphs differ from the graphs we would have if an object were in true free fall, if there was no air resistance. Then acceleration versus time would just maintain a constant value of 9.8. The velocity compared to time would just continuously increase at a steady rate. A constant slope on this graph leads to a constant value on this graph. And like we said, the vertical position versus time would continue to curve upward. Okay, so the real question is, what is the equation that describes the shape of this graph? Let's see if we can figure that out just based on Newton's laws. So if we have an object that initially just has a force of mg, ultimately has forces in opposite directions that are equal to one another, mg and bv, then, well, that's the initial and final. And we say final after how much time? Only as time approaches an infinite value, because after all, the acceleration is exponentially decaying towards 0, right? It never really gets to it, it just asymptotically approaches. And the same thing, this velocity never reaches the terminal velocity, it just gets very, very close. It takes an infinite amount of time for the free body diagram to look like this. So at any moment in time other than the initial value, the free body diagram would show a value of mg down and a smaller force of bv pointing up. So in that case, the net force is equal to mg minus bv. But we know we can substitute net force with ma. So ma equals mg minus bv. Well, let's see where we can go from here in order to try to determine what is the equation for velocity as a function of time. So in step 3, we're just going to substitute for a dv dt. So m dv dt equals mg minus bv. I believe that's the same thing as negative m over b times dv dt equals negative mg over b plus v. Or in other words, dv divided by v minus mg over b is equal to negative b over m dt. So we've just done some cross multiplying here, right? Okay, whatever we do to one side of the equation we can do to the other. So we can take the integral of both sides of the equation. We've got to match up our limits. So let's see, at time t equals 0, what is the velocity? I guess the velocity starts out as 0 at time t equals 0. And then, well, we could go up until t equals infinity, and then the velocity ultimately reaches the terminal velocity. But we don't want to work with infinite values. So if we just integrate starting from time t equals 0 up to any random value t, then the velocity has grown from 0 up to a corresponding value v. So let's see, probably the right side of this integral is easier to solve. So we'll leave the left side alone. The integral of dv over v minus mg over b is equal to, we can take the negative b over m out of the integral. And we're left with the integral from 0 to t of dt, but of course that just gives us t minus 0. Oh, and you probably know the solution to the left side of the equation. That's just going to be in the form natural log. But don't forget our limits of integration. So we have the natural log of v minus mg over b, and that's evaluated from 0 to v. That's equal to negative b over mt. Okay, so we have the natural log of v minus mg over b minus the natural log of negative mg over b. So the first expression came from plugging in the upper value of v, and the other expression came from plugging in 0 for v, and that's equal to negative b over mt. Well, you should know that the difference in any two natural logs is the natural log of the quotient. For example, the natural log of x minus the natural log of y is the natural log of x over y. So we'll take advantage of that to simplify our result. And we have the natural log of v minus mg over b divided by negative mg over b is equal to negative b over mt. Whatever we do to one side of the equation, we could do to the other. So we could raise e to the expression on both sides of the equation. And of course, e raised to the natural log of x is just x. So that's why we did this operation. So the whole left side of the equation becomes v minus mg over b divided by negative mg over b is equal to e to the negative b over mt. This is a long derivation, but stick with it. We'll end up with a result that very much verifies the equation, or I'm sorry, the graph that we guessed would represent velocity versus time for an object falling through the air. It's a shape that asymptotically approaches some upper value. So we're almost there. A couple more steps. If we multiply both sides of the equation by negative mg over b, and then, as we'll do two steps in one, after we've multiplied both sides of the equation by negative mg over b, we'll add mg over b to both sides of the equation. So we'll have v equals mg over b minus mg over b times e to the negative b over mt. So we can actually factor out mg over b. So we get v equals mg divided by b times the quantity 1 minus e to the negative b over m times t. Okay, and we'll stop here. So let's think about an equation of this form Well, we'll make a chart, t and v. So if t equals 0, we're going to have e to the 0, but anything to the 0 power is 1. So 1 minus 1 will give us a 0, and then anything multiplied by 0 is still 0. So that agrees with this data point, at least. Okay, then, well, I'm going to fast forward here. I'm going to jump to a very large value for t. We'll imagine a value of time approaching infinite. Okay, in that case, now we have 1 minus e to the negative infinite value. E to the negative large value is the same thing as 1 minus 1 over e to the very large value. Well, e to some very large value is itself a very large value, and 1 over a large value is basically 0. And so this whole expression is just equal to 1. And so the velocity is equal to mg over b. So that's the value of this asymptote, mg over b. Now let's think about this. At a very large amount of time, that's when the free body diagram shows the forces in opposite directions are equal. mg points down and bv points up. And so if we set those equal, bv equals mg, or in other words, v is mg over b. But because this is after a very long time, we say this is vt, this is the terminal velocity. So this expression mg over b just represents terminal velocity. Well, yeah, it should. So I guess we could actually write in a 13th step and simplify even more and say that velocity as a function of time is equal to the terminal velocity multiplied by 1 minus e to the negative b over mt, where terminal velocity is equal to mg over b. Now, if we want to get an equation to explain the shape of our graph for acceleration versus time, that should be easy enough. After all, acceleration is dv dt, so all we need to do is take this expression and take the first derivative with respect to time. Well, I'll leave it up to you to take out a piece of scratch paper and work through the steps, but it should be very easy to prove that a is equal to g times e to the negative b over mt. Okay, see if you can verify that result. Thanks for watching.